New. I'm in charge of camera system part.
Hello, I'm Zhang Mengjang in ECE 4534, Team 30. I'm in charge of ARM.
I'm Yifei Liu in Team 13 and in charge of the rover. We will first show our full simulation and then we will discuss about them separately for each part.
Before showing the full operation simulation, I want to basically describe how our system works. Our system has three stages. Stage 1, rover starts at an starting location and starts to move to the destination. Rover avoids any obstacles while moving to destination. Rover arrive at destination. Stage 2, rover stop temporarily and wait for operation of arm and the camera to be finished. Camera guides arm to find goal object placed at a destination. Once object detected, camera guides arm to move to the center. Once the object is at center, the arm starts to grab the object. After grabbed, arm drops object and stops temporarily. Camera stops as well. Stage 3. Rover backs to work, move to the drop-off place.
I will first talk about our design on the rovers. There are totally 5 threads in the rover design. One for the main thread, one for MQTT, one for SPI, and one for the motor controller, and there's also one for the parser. For the main thread, it just offers entrance for the program and starts the MQTT thread. Other threads are created in the MQTT threads after the MQTT is successfully connected. The rover cannot work with the bad MQTT. Once a JSON format message received by the MQTT thread, it will be sent to the parser thread. The parser thread will decode the information and then send to the control thread. The SPI thread will also send the encoded values to the control thread. The control thread is one of the most important threads in our design. The control thread will receive the information, the message, and then tell each motor their speed and direction. However, the motor controller thread cannot know whether the motor is working at desired speed. We have an encoder to get the actual rotated angles. A SPS thread will read 10 times a second with the help of a 100 millisecond timer. The control thread will analyze the value and adjust the speed of each motor. We have some special designs to protect the rover. If the rover should move at some time second, but the encoder value says not, it means that the rover hits the obstacle and it will stop and send error message to the other parts to tell them to stop.
For the ARM part, I choose to use ARM Uno 2.0, which has 4 SG90 servos. Each servo has 3 signals, PWM, VCC, and ground. The power and the signal is about 5 volts, and the PWM period is about 20 milliseconds. The duty cycle is about 1 to 2 milliseconds. The position 0, which means it's in the middle, it's 1.5 milliseconds pause, and And all the way to the right, it's about 2 milliseconds, and all the way to the left, it's about 1 milliseconds. These are the basic information of SG90 servo information. Next, I'm going to talk about ARM block diagram. As here you can see, the arm should supposed to be mounted on the rover, but due to the special situation of this master, we didn't do the integration. But we still did the integration of camera and arm. Here you can see there are 4 SG90 servos. Each one has the 3 signals G, 5, and PWM. G and 5 are directly connected to the CC3220SF. And the PWM comes from pin 64, pin 17, pin 2, and pin 1. And they are all connected through the jump wire to the PWM. There are also some pins that are connected to the logic annealer for the debugging. The CC3220SF has the Wi-Fi function, so it will use Wi-Fi function to transmit data with the broker. After this, I'm going to talk about the task diagram, which is on the software perspective. Basically, I'm going to talk about the of my code structure. As here you can see, from the beginning there's a broker. It will receive the and it will send the message to the receive queue. And the receive queue will receive this message and receive this message to the JSON parsing thread. And the JSON parsing thread will parse the information once there's a message in the receive queue. And it will parse it into a struct which contains distance, target, center, move edge, and index. All of them are in tab. And then it will send the struct to the Q2. For the Q2, there's also a thread called a motion thread. It will receive the struct. And based on the struct, struct contains this information. Based on this information, it will do the series of motion. Once the arm finish these motions, it will send the finish back to the broker. Yeah, that's all the basic information of my arm part.
Camera system has a well-designed IDE for users to write Python-like script to accomplish different functions. For this system, it uses SPI communication protocol as master, transferring sensor data to our MCU. The message sent from camera is designed as a bunch of integers that will be later processed as meaningful information. The first part involves the timer callback function with 1 second per reading. Then there will be a message sent to the timer event message queue to tell the MCU is ready to receive SPI reading from our camera. MCU receives message as a slave, then parsing a bunch of integers from master. The integer has been sent will be understood as the first is target, which indicates if there is a desired object appears in camera's vision. 0 means no object found. 1 means object detected. The next one is center, which indicates if the object is placed in the center view of camera's vision. 0 means object is placed on the side. 1 means object is in the center. Next one is move horizontal, which happens when the object is not placed in the center. Then a corresponding value to indicate which side the object is at. 6 means object is on the left. 9 means the object is on the right. The next one is distance, which returns a distance value of the object within 20 centimeters. The last one is index, which is used to help other components to check the validity of the data has been sent. After parsing raw data into a meaningful, readable sensor data, it will be formatted as JSON format, then later be sent into the object or information message queue. After that, the MQTT thread will retrieve JSON format data from that message queue and then publish to a specific topic sequentially.
For the constraints of our robot, the total cost is $130, $80 for the camera and $50 for the arm. For the compatibility hardware, for the hardware perspective, we use our Uno, OpenMV, and Rover, which is school provided. For the software platform, we use CCS, called Composer Studio. Third, power and energy. For the arm, it's 4.8 to 6 DC voltage. Typically, it's 5 volts. And for the camera, which is 230 mA and 3.3 volts. The rover, I don't know specific information, but it meets the requirement because it is school provided. So for the size, which is 50 centimeters times 50 centimeters times 50 centimeters. So the last part is functional requirements. So for our project finished the rover that can move to the given position and the arm can pick up and drop off. All the joints can move smoothly. And for the camera, it can detect the object's position and the cube's color.
We have some designs for the robustness of our system. For the rover, there is a SP controller implanted in the rover control part, so that the rover can deal with different ground situations. And the arm has a large grabber. It can allow few degree rotation errors, which means even if the arm is not at an accurate position, the arm can also successfully grab the cube. The camera has a well built-in SPI function call. It can ensure the robustness of the camera system so that it will send the sensor data continuously till power off. The other part is on how MCU captures sensor data and handles it. We have used a well-designed timer callback function to capture SPI reading and message queue to start messages in a way that will not cause tasks suspended in the system. However, there are some situations that our system cannot handle. If the rover is working under low speed, it may trigger the error detection and stop all systems. The arm is not long enough, so that the rover should be stopped at a great position, and the dark environment can affect the camera data greatly.
Reliability on rover. The primary function of the rover is to move and rotate with certain distance or angle from the input. The distance or angle are calculated by the encoder values. The distance is directed proportional to the number of cycles rotated by the motor. The rover will stop till every motor rotates to the desired cycles, and the controller will adjust the motor speed if the speed too fast or slow compared to other motors, or motor to move straight or rotate ideally. Reliability of ARM is that 4 servos can rotate correct degrees. The SC90 servo has 3 input signals: VCC, PWM, and ground. The VCC needs to be connected to 5 volts and PWM needs to be 0 to 5 signal. To make the arm rotate to the desired angle, we need to provide the correct duty cycle. For example, 1 millisecond is negative 90 degrees and 1.5 milliseconds is middle. Therefore, as long as we convert the desired degree to the duty cycle, the robot will move to where we want it. The reliability on camera. The function of the camera is to find if the goal object appears and where the object is placed as user desired. The camera has high confidence to accomplish those functionalities. The camera has a section to allow users to find out the desired color threshold by simple means where well-designed OpenMV IDE. The camera can correctly return location information and draw a rectangular visual box along the goal object based on the location of the object that the camera detected.